So we're going to do a quick recall right off the bat. Even and odd. What's up? What's up?
Everyone else did it.
Yeah. I already collected and entered grades, and I'll come grab it, Matilda. Everybody passed it forward, and I came around and collected them. All right. So we have this idea, and this is a recall, but we have even functions and odd functions. As we're looking at these, they have to do with symmetry of some sort. And I can think of like a million places that this applies, and it's going to be very helpful when we graph our trig stuff. So these have to do with symmetry. And what I'm going to write up here is I'm going to write just the definition of them, and then I want you guys to help me figure out whether, like, where our symmetry exists. So I know that whether we're checking for even or odd, we always begin by checking f of negative x. So I'll do it on both of these, and notice I'm just doing both of them simultaneously. If a function is even, if I plug in negative x, it gives me the same thing as if I plug in positive x. Okay, now, with just this, I want to think about what this really means. So we're going to draw a small little graph, and I'm just going to plot a couple points. And I'll probably plot more than a couple realistically. I'm going to plot a point at here. Then I'm going to do a point here and here. And I'm going to make it look kind of like a wave. So I'm going to actually do that better. I'm just going to make it look wavy. So something like this. I know it doesn't look super wavy to you right now, but if I do this, does it start to look kind of like a wave? A little bit maybe. Okay. If I've plotted all these points at x, if I get the same y value when I plug in negative x, where do these reflect? Do they reflect like this, or do they reflect like this? And if you're struggling to make sense of this, let's just pretend these are numbers. If I plug in a 1, it spits out a 1. If I plug in a negative 1, it should spit out a 1 again, which means this point would be right here. So as soon as I put, and I'm going to do this one in a second color just so it really stands out. If I plug in 1, I get this value. If I plug in negative 1, I get the same value. What does it look like I just reflected over? The y-axis. And what I wind up seeing is a shape that's going to look something like this if I do it. Now, does what we just graphed, without having 1 and stuff, does this look like something you've seen before? It kind of looks like a parabola. Does it look like anything else that you've seen? A wave. And when have you guys ever, you're right, it does look like symmetry also. When have you guys ever graphed waves? Hey, this is one of our graphs. And I didn't put the scale on here, but this is what it means to be an even function. It turns out there's a couple of flavors that are going to be even here for us. Looking at this, our even, is it the word flavor that makes that weird? Yeah. Okay. No. This, yeah, different. We have 2 even functions that we're going to deal with. The first is cosine. And you can just write cos if you want to. Cosine is even. Now, if a function is even, would it seem reasonable that if you just flipped it, it would also be even still? And what's, if you take cosine, which is the x or the y coordinate? X. Remember, x, y is alphabetical. Cosine sine is alphabetical. This is the x coordinate of each of those points. If you did 1 over x, how did we define that yesterday? And you might have to look at your notes, because we said cosine is x. 1 over x is secant. So we get 2 even functions out of these trig ones. It's secant and cosine. And really, I only care about cosine because secant we just get for free once we have cosine. Okay, with all of this, we have that cosine is an even function. And there's a reason that we care about that. We'll talk about how we graph these, and I'll show you the way that I graph them. But let's see if we can't recall on this other side, if it's an odd function. Instead of it giving me the exact same thing, when I see an odd function, and I'm just going to sketch this for us, and maybe this would be a different function, and I don't care if you know which function it is. I'll switch colors so I can see it. We'll do green first, I suppose. This function right here, if it keeps waving, if I plug in this x, it comes up here. Now, if it were even, it would be up here again. But I'm not in the even section, I'm in the odd section. So instead of f of negative x being the same value, do you remember the change that it makes? If it winds up not, it can't reflect here because that wouldn't be a function. It can't go over the x-axis, but it could go over the origin. And if I did that and I reflected it over the origin, it looks like it'd wind up down here, and I'll do that one in blue. If this is x comma f of x, this is negative x, and what's the y value? Negative what? Good. This is what it meant for a function to be odd. We see that if we plug in x, we get the exact opposite if we plug in negative x. And we would get a wave that looks like this instead. Now, this one would keep going, so forth and so on, forever and ever, just like our trig functions will. And what we see here is something like the graph of not cosine. And if you take out your unit circles, we'll even connect it, whether it's the big one or the cheat sheet. We're going to see this evenness show up right now. So take them out for me, and we'll look at them, because we're going to use them anyway. Don't think planes are landing today, huh? But I do think there's 3 charters coming in tomorrow is the plan. And then I hope they have like 10 illusion flights. Okay, check this out. Let's pick a positive angle. Let's pick pi thirds. There's an easy positive angle. What's the sign of pi thirds if we look at our unit circle? So that's the same as 60 degrees. But when I say the sign of pi thirds, you should do 2 things. You should find pi thirds on your unit circle, and then you need to look at the x value or the y value if we're talking about sign. So look at your unit circles at pi thirds. What is the y coordinate? Okay, so that's sine of x, right? Or pi thirds. Now find negative pi thirds, which is just going clockwise instead. It's the same as 5 pi thirds if you go all the way around. What's it there? Is it still root 3 over 2? What is it? Is it exactly what we see happening? If I plug in f of negative pi thirds, is that the same thing as negative pi thirds for sine? Like we get the same value, just opposite sign, right? I can verify that it's odd there. What if I do it for cosine? What if I do the cosine of pi sixths? So here I am at the cosine of pi sixths. Sorry, it's just barely up. What's the cosine of pi sixths? And if we do cosine of negative pi sixths instead, which is right down here, what is it? Root 3 over 2. Do we get the same thing? Which is exactly what it meant to be even. Addison, you might have zoned out there for a second. Did you zone out, or were you not sure what I was saying?
No, I accidentally zoned out.
Okay, so just to make sure we have it, I just want to show you. No, you're good. If I go to 30 degrees or pi 6, do you agree that the cosine is root 3 over 2? So that's positive pi 6. If I go to negative pi 6, do I get the exact same x value?
Yeah.
So cosine stays the same, which is what it means to be even. And then we do the same thing, but we see this happens here. It happened with sine. It was odd. Pi thirds and negative pi thirds give me opposite values. Okay, so we have just determined that sine of x is an odd function. If sine is odd, so is its upside down. Cosecant of x. Okay, this one, we're going to work out a tangent somewhere. Let's calculate a nice, easy tangent. On your unit circle, I don't care if it's on your cheat sheet or the big one that we've done, what's the tangent of pi fourths? It's 1. And that's so nice because it's root 2 over 2 divided by root 2 over 2. What's the tangent of negative pi fourths? So instead of going here, we're going here. Is that even or odd? It's odd, right? Because if I plug in one value and then I change it to a negative, the whole sign changes. It means that tangent must also be an odd function. And what else is odd? Cotangent. And I know I'm being super inconsistent with how I'm writing these. Very intentional. These all represent the same. You will never see me write the full words, except for this one situation. All right. Do we feel okay with that? Now, if we look at the larger picture, and we'll just do this real quick. You guys have seen what sines and cosines look like for sure. Everybody, we're just going to play the trust game. Close your eyes real quick. Okay, keep them closed, keep them closed, keep them closed. Okay, I have 2 graphs on the board. Red and blue. Which one is sine and which one is cosine? And how would we even work it out? You can open your eyes, Leigh. I'm sorry, I didn't specify that. How would we even determine? Because they both kind of look the same, right? Like if you've ever seen, if you watch a lot of, anybody watch like Grey's Anatomy or doctor shows? If you ever hear sinus rhythm, when they're talking about the heartbeat stuff, you'll talk about, oh, we have a regular sinus rhythm. They're not talking sinus like your face cavity. They're talking sine like this. Sinusoidal means it's doing this. Like if you look at a heartbeat, go beep, beep, and it does that, right? It follows this wavy shape, just worth seeing. Back to our other question, though. Which one's sine? Which one's cosine? How could we work it out? Why is cosine red? Okay, so I love that justification. This red graph is just folded over the y-axis, right? The red graph is even, and I can see because it just says this. That is my cosine. Another way that we could convince ourselves of that is if you go 0 degrees or 0 radians, here I am. What's the cosine of 0? Look at your ordered pairs. What's the x value of this ordered pair at 0 degrees? What's the value of this function at 0? And there's my cosine, and I can sort it out that way as well. I like your way better. If we look at the blue function, does it just reflect? If I plug in pi halves, if I plug in negative pi halves, does it just switch? Hey, and that's odd, like we just saw. We can see these graphs represent exactly these. Okay, as we get going through, if we're going to be talking about these functions, we better think about them as functions. So our second, and like this is all kind of just preparation for it, we've dealt with a lot of the intuition that we're going to need. This is our second section of 4.2, and the rest of it's going to go much quicker. So we're going to talk about these trig ratios as functions. I really like trig stuff. This is the most valuable modeling stuff that we'll get because most stuff is not nice and linear or quadratic. Most things do some sort of wavy motion. Like the universe as a whole, everything is just wavy. All right, if we're talking about any functions, and we've dealt with a lot of them this year, what are some of the natural things I might ask you about? Do I ever ask about what x values can I use or which y values can I use? What do we call all the x's that plug into a function? Domain. What do we call the y values? The range. Now, there's something else that happens with these, but let's talk about these functions for a little bit. We're only going to look at sine and cosine right now, for at least the time being. So right off the bat, we'll say, here's our sine, and I'm not going to make it capital. I'm just going to use lowercase. We're going to have two functions. We'll have f of x is the sine of x. And then over here, in just a moment, we'll come back and we'll fill all these in. But we're going to have f of x is the cosine of x as well. Now, we could use x or theta. It doesn't really matter what we're using. These are just our variables. But let's see if we can't make sense of some of these things. For these two, let's think about the domain of sine. And we'll just do this on each of them. So the domain. If we look at our unit circle, can you give me an angle that I can't figure out the sine of? Like, could you do 0 degrees or 0 radians? Could you do 13.7 degrees? Is there any angle that you can't plug in? Like, it's just defined as x, right? Is there any value that we can't plug in then? So I think we're okay with negative, because if I say let's do negative 10 degrees, it just, instead of coming here, we just do this. So I can go positive or negative, right? Which means we're going to have a really hard time finding anywhere that breaks my sine function. If there's nothing that we can find, what's its domain? It is all real numbers. Is the same thing going to be true of cosine? I can do cosine of 0 and 13 and negative 20 and like any of them. So just the same here, we'll say the domain of cosine is also just a set of all real numbers. Okay, we're just looking at the parent functions right now, and then we're going to get something that we haven't seen yet this year, but I assume you've heard. If we talked about the domain, we're naturally going to talk about what? The range also. Now, what gets kind of misleading, and it's a natural place to get goofed up, is we talk about sine and cosine being y, and x respectively. When I say the cosine of x or the sine of x, you're going to be tempted to only look at the x's. Just remember, it's just what we're plugging in. If you look at sine, is that the x coordinates or the y coordinates on your unit circle? The y coordinates. What's the smallest value that ever shows up anywhere on your unit circle? If you go the whole way around, I'm going to start spinning my arm like I'm playing a sweet air guitar here. And I want you to tell me to stop when I get to the lowest part of sine ever. What's the lowest y value? This is the lowest it ever gets, right? What's the smallest value that we ever have? Look again. Look at the y coordinate at the very bottom of your circle. That's the lowest we ever get. It's -1, right? So I can get all the way down to -1. And what's the biggest I ever get? It's going to be up here, right? So if we look at what will it spit out, we see the smallest is -1 and the biggest is ever +1, which means we're telling what does this function spit out. You're giving me the range. The range of sine is the set of all y values such that, what was the smallest it could ever be? Is less than or equal to y. And y is always smaller than or equal to what? 1. It goes everywhere between -1 and 1. Now, this is where it gets weird to think about. If we look at cosine, and I know we're going to look at the x coordinates, but that's our output. We plug in an angle and it spits out the x value. Like, that's it. What's the very smallest that cosine ever gets on your unit circle? Anywhere on it, the smallest x value that ever shows up? -1, and it happens right over here, right? What's the biggest it ever gets to? Over here, and everything in between gets hit, right? Which means our range then for cosine should be what? The same thing. Only thing I'm going to do is I'm going to write it a little bit different. I'm going to say the range for this one, and just because we can, is a set of y such that y is in the interval from -1 to 1. You can write it in pure set builder, just like this. I'm just showing two different notations. These say the same thing. They have the same domain. They have the same range. Okay. The last little piece. Have you guys, or rather, do you recall talking about the period of sine or cosine? Does that sound familiar? Okay, so there's a whole lot of estrogen in here, and it's a natural connection to make. Things happen in cycles, right? Like whether if you're talking about like anatomy and stuff, it's a cycle, is how we refer to women stuff. Okay, right? Like everybody okay with that language? It's called a cycle because it keeps doing what? It's cyclical and it keeps happening at the same interval, right? Like that's why we call it. We talk about the cycles of the moon as an example, or the cycles of the planet, where we talk about what season is it based on where it is. When we look at these functions, we get that same cyclical behavior happening. And I assume that in English, it probably comes from math idea as well. But when we're talking about any particular cycle for these things, if I look at just these graphs, is there a place that if I cut just some of it, I could just pick that whole thing up and just put it down again and again and again, and we get the exact same graph? Like if I just copied this, that doesn't work, right? Because it'd just be boom, boom, boom. That wouldn't do it. So what I'm going to do here is you guys are going to help me build up my graph. I'm going to take the numbers off of these, and I'm just going to do a little copy paste here. And I want you guys to help me pick, where should I pick this thing up if I want to be able to copy it again and again and again and get this whole graph? Where do you want me to start copying? At the y-axis, like right here? Okay, and then you tell me, how far do I go? Do I have to keep going? Okay. If I go all the way to here, if I pick that up, I don't know that I need to go that far, but let's check. I'm going to try that one, and let's just check. If I start putting this down, do they connect together and look like I would expect it to? Was there a smaller section that I could do that with? Could I have done it with less than that? How far do we go around the circle before we get back to where we started? Ooh, careful. It's not 1. At 2 pi, which that'd be like 6.28, right? Okay, we went to here when we did it. Oh, we're doing cosine. I'm fine with that. Now, if we look, is this the one we just did? Oh, I might be wrong. I lied. I'm okay with this. I was thinking that we're on the different one.
Wait, I really don't understand
Yeah.
how getting small.
So I'm cool with that. We can't make it any smaller. I was just wrong. Looking at this, we all agree then that this is the smallest section that I could copy and it would just repeat itself over and over, or it would just cycle back through. What's the distance that I've gone? If I look, I went from here to, we went to up here, right? And if I just look at it, that's a little bit less than 6.3. 6.28 is my guess. Is that a special number? It's 2 pi. We just saw that this function runs 2 pi before it repeats or cycles again, right? What we have just given ourselves with this is what's known as the period of sine or the period of cosine. It's just how long is that smallest cycle until it repeats. So we'll just define it here real quick. We'll add the period of these, and I'm going to move it down just a little bit. The period of sine or cos, we should probably look at sine since that's one we're trying to deal with. Y equals sine x eventually. If I start at 0, how far do I have to go till I can repeat it and just pick it up and copy it again? Doesn't work there. Is it still 2 pi? We still have to pick it up there. So what we wind up seeing is whether it's sine or cosine, it's just 2 pi. That's how far we have to go before we repeat our function. Now, the periodicity of functions, we can make it so it's not sine and cosine. We can do some wonky ones, but I'm not even going to write it down. It's the smallest interval for which this happens. And I was wrong when I said I think there's a smaller one. There wasn't. There's bigger ones that would work. Like I could do 4 pi and just pick up 2 halves of it and keep going and double it. But there's 2 pi is the smallest section where it repeats over and over and over. So we have gotten the periodicity of these things. Now, the reason that we care about the periodicity is it's going to make stuff super easy to calculate when they don't show up on our unit circle. And we've already kind of been using this idea. So we're going to do one last example. And I can tell that eyes are starting to glaze a little bit. We're almost done, I assure you. We're going to use periodicity. Now, as I said a minute ago, we've been using this the whole time. If I give us an angle, and I'll give it to us right now, like let's say I wanted the cosine of 9 pi halves. If you have a unit circle in front of you, I don't know that it's going to help a ton right now. Why? This is not on my unit circle, right? But if we know that every 2 pi radians, it just repeats itself and cycles back through, how much do I add or subtract to this to be able to make it show up on my unit circle? Any number of 2 pi, right? 2n pi is how you could say it. So if this number 9 pi halves is not on my unit circle, can I just try to move it a whole period over? And you would never write this, with the exception of right this second, is going to be the only time I'll ever write it. Is this the same, question mark, as if I did the cosine of 9 pi halves minus 8 pi halves? Is this the same? Why? What's the period of sine or cosine? 2 pi, which means every 2 pi I get the same value, right? Whether I move to the right or to the left, it doesn't matter. Did I just move 2 pi away? Not exactly, but did I move 4 pi away, which is just like doing 2 pi twice? So I've just gone 2 periods to the left, right? Or 2 cycles, however you want to word it. When I do this, this is the same. Yes, absolutely. Because I've done, well, we can try one and see if it shows up. If I do 1 cycle, it'd be 4 pi halves, right? And I would get, this would be the same as the cosine of 5 pi halves. And on your unit circle, where is 5 pi halves? But we could try it and then realize, oh, crap, we're still too big. And what would we take off this time? Go another period to the left. Yep, and then what that ultimately does, it's the same as if we had just gone 2 periods left initially. Okay, so we just subtract until we're on the circle. This value is gross until we realize it's just cosine of pi halves. And what's a cosine of pi halves? I heard one person say it, but I want everybody to say it. 0. This periodicity, we've been using it anytime that we've thought, oh, we're too big, we need to go backward. We've been using it. Now, where this stuff shows up, and I don't love these problems, but I just want to show you because I imagine we'll find some AP ones that look like it, is this function periodic? Like if I had it keep going like this, is there a clear periodicness of this function? And we could pick out that it's probably, and I'm just going to eyeball it here because I didn't do it perfectly, but I think that if I just pick up this piece and I move it over, it'll probably work, right? And I was off because I just eyeballed it. But we can see the periodicity happening here as well. I prefer to just do it with the sine and cosine rather than these goofy wonky ones. Okay, trig stuff. Feel okay so far? Name of that famous Lakota chief? Good. All right. I'm going to give you guys 12 minutes to start on stuff. So we get homework 4.2.2, which you will find waiting for you on page 277. Do we have a class meeting today then? Okay. We do, right? Did I email you back fast enough? Okay. Page 277, I want you guys to do 32 through 38, 43 through 46, and 49. Now, we're going to try it. I want you should do at least one from each section, but I want you to trust your judgment. If I think it will not hurt anybody to do all of them, but I understand you guys probably have some other stuff going on in all your lives as well, I assume. It's not just all pre-calc all the time. So I'm going to trust your judgment. Do as much of it as you need to, as long as you're knocking out and trying each section. Get the practice that you need. Cool.